Thanks. I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just help us to understand a little bit about vector bundles and fiber bundles and so forth, and just try to understand as much as we can in the time we have, Lord. You know, I pray. Amen. So I think a pretty good place to start in terms of just bundle constructions is the tangent bundle. All right, so what's the tangent bundle? So what I will foolishly attempt to do is to describe what the tangent bundle looks like. So we're going to be working, you know, we got some manifold M. Let me make it, that's too exciting, a manifold. Let me fix that. Get a manifold. It's not a very good picture, but a manifold M. All right, and so the idea of the tangent bundle is to pick, you know, each point in the manifold, basically, and above that, you know, attach a copy, if you will, of the tangent space at that point to M. And then you think about doing this over the whole, you know, the whole manifold, and that gives you this tangent bundle. Now, it's not actually TPM up here. It's something more interesting than that. It's like TPM. But I guess formally speaking, the tangent bundle is, as a set, it's the disjoint union over P and M of TPM. All right. So you just glue all the tangent spaces together. And so the way to describe something in the disjoint union is something like this. I mean, basically, you can look at that as pairs P comma V, such that V is in the tangent space to M. Anything in there looks like that. And so we have a natural projection that goes from the tangent bundle, you know, down to the manifold. In particular, pi of P comma V is just, well, P. So pi is a mapping from the tangent bundle to the underlying manifold. Now, what's a manifold? A manifold is a set which locally allows you to do calculus. In particular, it's a set with an atlas of charts, which are bijections to Euclidean n space, let's say, such that the composition of two charts, when we look at the transition functions from one chart to another, we get a smooth function. That's what it means to have a smooth manifold, right? So if I was to clutter this picture up a little bit and to try to draw, well, let me not. So just a reminder, on the manifold, right, if we have U and another one, let's say U bar, then, you know, we've got coordinate chart X, we've got coordinate chart X bar. This would be to, you know, well, let's say Rn, of course. So going from here to here, we're looking at what map? And so in particular, you can look at the overlap of the charts right here, right? So that would, I don't know, it maps down to here, and that will map over to here somewhere like that. I don't know what exactly. Not going to be so fussy, but the overlap of the charts, U intersect U bar, supposing that they're, you know, you pick a point in here, there you can compare the coordinate system, the X versus the X bar coordinates, and how should they compare? What's the map that relates these two? is so much easier than what we were just trying to do. It's messed up. Anyway, like that, right? So I want x bar inverse composed with x. See, because, oh, I'm an idiot. Try that again. X inverse, composed with x bar. There we go. So that would be the so-called transition function on the manifold. So this x bar composed with x it needs to be a smooth function on Rn. I'll put some quotes around that. I don't really mean on Rn, I mean on an appropriate subset of Rn as is dictated by the particulars of the overlap. It needs to be smooth where it's defined. So let's just say it's, well, it's C infinity on Rn for functions with compact support in the appropriate region. Compact support is just a fancy way of saying that the function is only non-zero where you're interested in, and it's zero everywhere else. Which is a fancy way of saying I don't care about domains, so I'm going to use some intimidating language to confuse students. And if that works for you, well, very great. I seem to have lost my inverse. All right. Now, one of the things we learn in manifold theory is that there is a chain rule. And so you can calculate the differential of x bar composed with x inverse. And what do you think you get? You get the differential of x bar composed with the differential of x inverse. And, or, if you like, you could say something like this. If I take the coordinate derivation partial x, let's say upper I can rewrite that as a sum j equals 1 to n of partial x bar j partial x lower I partial x bar j. That's actually the coordinated version of what I wrote right above it. When you sort through what the chain rule means for the compositive differentials of the transition of the coordinate charts, and you look at what that actually says about push forwards of the coordinate vector fields, it says wonderfully that when you change coordinates, it's just like the chain rule. So if you want to switch your vectors from the x to the x bar coordinate system, you just have to basically follow a formal chain rule in some sense. Change your partial x's to partial x bars according to this rule. And this is actually, this guy actually is like the Jacobian matrix for the transition. It's like the Jacobian matrix for this, or something like that. I mean, I'm being a little bit, again, put some quotes on here because I'm not being careful enough at the moment, but basically when you sort through it, you'll find out that those, if you were to put them in a matrix, that's the matrix of the Jacobian matrix that you get from the transition functions. Okay? So my point is, when we study manifold theory, we learn how to change coordinates on vectors at a point. Right? So what is, and we also learn about coordinate charts, right? Like the atlas on M. What's the atlas on M? It's something like we have, you know, the charts and the chart domains and the charts, such that what? And maybe you can stick a little sub alpha on them or something, right? So the union over alpha in some index set, let's say lambda, of U alpha is the whole manifold. And, you know, X alpha is a mapping from U alpha to Rn for all alpha in, you know, the index set lambda, where X alpha composed with X beta inverse and X, you know, beta composed with X alpha inverse for all alpha not equal to beta in lambda with U alpha intersect U beta not equal to empty or smooth. this is just me. This is a fancy way. I mean, it's the details of what I mean when I say that the coordinate charts on a manifold are compatible. That means in as much as they can be compared, they're compatible. They agree on what is smooth. There's smooth function, transition function to get from one to the other. And by default, if the coordinate charts, if the domains don't overlap, then those are just by definition compatible. All right. So for example, any vector space, take your favorite global coordinate chart, there you go, a manifold. There's only one chart in your atlas, great. Now for logical reasons, sometimes you want to work with a maximal atlas. A maximal atlas is the set of all possible compatible charts with a given atlas. So a set paired with a maximal atlas forms what's called a differentiable structure. All right, and a differentiable structure is unique for a given atlas. There's a unique maximal atlas which a given atlas will be completed to. But for a given point set, you could have different differentiable structures. So one of the kind of shocking things is they've found different differentiable structures on higher spheres. Well, there's more to that story. But anyway, this story is particularly interesting in dimension 4. A lot of different differentiable structures we found in dimension 4, maybe less so in other. Let me stop talking about that. I don't know enough to say anything decent at the moment. So, okay, so that's an atlas on M. So to describe the tangent bundle, we have to give an atlas on Tm, right? Because a tangent bundle is itself a manifold. It's a new manifold. So, describing what we mean for a, so, if we were talking about manifolds more completely, I'd also define for you, like, what does it mean for a function from one manifold to another to be smooth? I should probably do that for just a second. What do we mean by, if I've got M, right? I've got a function, manifold function from F to another manifold N, and then when I say F is smooth, what's that mean? That means that if you pick a point P, and you look at its image F of P, then you can pick some neighborhood U here, neighborhood V here, such that this X takes you down to X of U, and this here takes you down to Y, the Y coordinate chart in the range takes you down to Y of V. And then if you look at the local coordinate representative of that F, right? What do we mean when we say F is a smooth function from manifold M to manifold N? We mean that the local coordinate representative of F is smooth with respect to the appropriate choice of local coordinate representatives at each point in its domain. Which is to say that this map is smooth, which is to say Y composed with F composed with X inverse is smooth. And the actual details of that basically amount to looking at the jth component of F with respect to the ith component. That's the Jacobian matrix, if you will, of that function with respect to those coordinate systems. So if all of those are smooth, that gives you the F is smooth. But anyway, smoothness. And then you have to be able to repeat this story, sorting through, finding a choice of local coordinate systems at each point in the domain. They don't have to be the same one, but you have to find one. You can, easy exercise, if you've got smoothness with respect to one local coordinate system, you automatically get smoothness with respect to another because you can change from one local coordinate representative to another by doing stuff like this. Right? So this is equal to that, but this is the local coordinate representative in the new system, new coordinate system, and this is a transition function, which is smooth. So composite of smooth is smooth, 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 smooth. Okay, enough. Anyway, we can talk about manifold smoothness, and then, so the point is, while I used M and N, we could just as well in our thinking, write Tm and whatever. Well, I could have just left it as N because I haven't used N for anything else, but the point is if I can describe the tangent bundle as a manifold, then we can think about smoothness of maps to or from the tangent bundle, just like we think about smoothness of maps from the manifold, right? So then the question is, what is the atlas on the tangent bundle, right? So really, the first question is, what's a coordinate chart on the tangent bundle, right? So how about this? We pick a point, right? You take some neighborhood which contains the point in the atlas of M. All right? Suppose you've got a coordinate neighborhood. So what's that come? So this U, you know, where, what's my notation? U comma X is in the atlas of M, right? So we're going to get some space up here. Let's say pi inverse of U. Pi inverse of U is a subset of the tangent bundle. What is that? That is things of the form P comma V such that pi of P comma V, which is equal to P, is in U again. So in short, it's things in the tangent bundle which have their point of attachment as fitting inside U. So first of all, we're going to set U tilde equal to pi inverse of U. All right? That's going to be my domain for the coordinate charts. And then I need to figure out what is x tilde of P comma V going to be equal to. So let P comma B be in the tangent bundle. How should I define the coordinates of P comma V? So first of all, this is actually, yeah, what I heard x of P. I like that, x of P, that's good. But what about this pesky V over here? How about this? V of x1, V of x2, V of xn. Well, I really should write upper 1. Sorry, I'm trying to, I have problems with notation at this point in my life. And technically this is the vector, VP, I don't know what notation you want to use. The point is that this V is an element of the tangent space to P of M, which is understood to be the derivations on the smooth functions at P. So any derivation, remember, if V is in the derivations of the point, these guys, then we can rewrite V as the sum over V acting on the coordinate functions times partial xi at the point P. And sometimes we'll put a P here to emphasize that we're evaluating at P if we're thinking about those more generally as vector fields or something. I don't know. You get too many P's floating around, it just drives you nuts. I'm going to erase them. Whatever. The point is that's a set of n numbers which uniquely describe the vector attached at P, namely V. Those are the components of the vector. So that's how we get the tangent bundle. So there's the coordinate system of the tangent bundle. We take the coordinates of the point paired with the coordinates of the vector, and that gives us this new coordinate system, x tilde, if you will. So x1 of P, da, 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 da. So how many is that? That's in R2n, right? So the tangent bundle is a 2n-dimensional manifold, whereas the manifold was an n-dimensional manifold. Any questions? By the way, this kind of thing, u tilde comma x tilde, sometimes called an adapted coordinate chart. There's some abusive language here going on. Well, anyway, all right, so we good? This u comma x in my current language is a coordinate chart? Yes. So we can take any coordinate chart on the manifold and sort of bump it up to a corresponding coordinate chart on the tangent bundle. And I think you might not be surprised if I were to tell you how to construct a cotangent bundle at this point. Like, what would a cotangent bundle be? It's not the dual of the tangent bundle. It's something more point-wise. It's the disjoint union over P and M of the duals. I mean, maybe I could write. I mean, it is not just 1 over the tangent bundle. So many things I want to say to you right now, but I can't. I'm bound by the Liberty Way to forbidding me certain phrases that I would like to use, but I'm forbidden. But in any event, yes. So this is essentially just gluing a covector, the set of covectors at each point over the manifold. And so here, if you were to describe the adapted coordinates on this guy, so you're looking at p comma a 1 form, right, or a covector at a point, you can guess what you're going to do. You're going to do x of p, and then alpha 1, alpha 2, dot, 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 alpha n, where those are the components of the covector with respect to the coordinate system x. And so the cotangent bundle is also a 2n dimensional manifold. And if you see what we did here, you won't be surprised when I tell you that you could just as well build the tangent bundle for, say, I don't know, K-forms. What would you do? You would just think about the disjoint union of K-forms at each point, and you'd use the adapted coordinate system. You pick, you take x to pick out the point coordinates, and then you use the components of the form pointwise to give the coordinates of the rest. Don't ask me what the dimension is. I mean, the dimension of this is kind of complicated to explain. But you could just as well talk about a tensor bundle, right? You could attach a tensor at each point, use the components of the tensor to fill out the rest of the adapted coordinates. All right, that's the basic idea of a tangent bundle. And you can prove that these adapted coordinate systems are smooth on the overlap. The proof that these would be smooth on the overlap is something I did on tests in my manifold theory course. It's not that bad, really. When you look at the composite of like an x tilde and a y tilde, what do you end up with? Well, let's say x bar tilde in my current language. I'm going to do y instead of bars. It's easier to read. So when you look at this, you end up with stuff like x composed with y inverse. And if you were to look at, another way you could look at this second piece here is really what you're doing. What is this? Another way to look at it is just dx acting on v, p. And the reason that makes sense is x, working myself out of commission here. So this makes sense because x is a coordinate mapping from u, which is a subset of m to Rn, right? So dpx is a mapping from the tangent space at p at m to Rn, identifying Rn with its tangent space. So this is straight up the differential of the coordinate map pushing the vector forward. The push forward of the vector under the coordinate maps differential is actually the coordinates of the vector with respect to that coordinate system. But this identification is super nice when you're looking at this, because when you look at the transition functions, you end up looking at something like the differential of x composed with y inverse, which then is still smooth because it's the differential of a smooth thing, which is, anyway, you can prove that these compatible charts are in fact, you can prove that the adapted charts to compatible charts are in fact themselves compatible. And that makes a great exercise for like an entry-level manifold theory course in grad school. So I'll leave it to there. And really, the purpose of this lecture and the next is just to try to give you guys just enough information to give you some sense of how things are done, and maybe just enough to get you into trouble. At this point, there are excellent books to fill in the details. Lee's Smooth Manifolds book is amazing. Jeffrey Lee's Differential Manifolds book is also amazing, but kind of a different flavor. And there's Tu's book on manifolds. There's just so many different things these days. I mean, there must be a dozen really well-written, accessible manifold theory books that you can fill in the gaps I'm creating. So what's the purpose of the tangent bundle? I mean, yay, we created new manifolds. But what's the real purpose is to talk about vector fields, right? What's a vector field? Vector field on M. Yeah, it's an attachment. Would you say attachment or assignment? Yeah. Of vector at TPM for each P and M, right? What's that? Smooth attach. Yes, a smooth attachment too. We'd like that, right? And better just be one, right? Just one. So enter the definition of the section of a bundle. What's the section of a bundle? Trying to be careful here, so I got out my book. Oh, it's too careful. All right. Well, this one's got principles. I guess it'll still work. Oh, I did. As soon as I open a book, I get myself into trouble. Stink. Well, anyway, let me try without the book. So the way I picture it is something like this, guys. So here's my stupid picture of a manifold and the tangent bundle over the manifold, right? And so I mean, this isn't quite accurate, but imagine that you pictured vectors transverse to the manifold instead of tangent to the manifold, which wouldn't be accurate because the tangent vectors really should be tangent to the manifold, right? But for the purpose of my picture, if you don't mind this abuse, here's a stupid kind of way of visualizing it. All right, so this would be some sort of stupid vector field. And here I could put maybe I put the 0 draw the 0 for the tangents up here like that. And so this section starts here and eventually it goes through 0 like over here. So something like, I don't know. So if you can imagine this is just a sort of a, that doesn't quite do it justice. The point is, and that's not exactly the section either yet, but the point is this purple thing, the red thing I just drew, if I looked at any point here, I'm trying to get the idea that above that point, right above that point, it just intersects that the intersection of the fiber over P. So this would be pi inverse of P, the fiber over P. That fiber just hits that section in one point and only one. So a typical point up here in the fiber would be something like, typically use something like S of X. If this, X is, we're using X for other stuff. Let's say S of Q. Suppose Q is a point down here, then that would be S of Q, all right? And for that to make sense, what I'm really saying is that pi of S of Q is what? It's Q again, right? So this is the condition I need for the section. I need that pi composed with the section, right, is equal to the identity. Or let's just say 1. And I could also talk about local sections. I could talk about a local section. A local section might be something like, I've got just this little u, right? And then a local section would be something like, here's S of u, where S is a mapping from u up to the tangent bundle, right? Such that pi composed with S gives me the identity on u. But what is a section, right? Interpretation. What is a section of the tangent bundle? Well, S of Q is Q, comma, V, such that V is an element of TQM, right? In other words, we've attached a single vector to the point. So a section of the tangent bundle is a vector field on the whole manifold. A local section would be a vector field just on part of the manifold. Does that make sense?
So it creates a field for each point on the manifold, basically.
Right. Yeah, a section of the tangent bundle is uniquely identified with a vector field on, I would say uniquely identified. Some people would say it defines a vector field on the manifold. What do you mean an attachment of a vector at each point? What does that even mean? Well, this gives a home to that idea. And Kang mentioned it should be smooth. How do we capture smoothness? Well, how about of manifold maps? Smoothness of the vector field is completely captured in saying that this is smooth. In other words, it's a smooth map from U, which by the way is a manifold. If you take an open subset of a manifold, it's naturally a manifold with respect to the restriction of the atlas to that subset. You can always take a subset and restrict to a subset. It's a manifold. U is a manifold in its own right. And so manifold, smooth map on a manifold makes sense. It's a technically defined thing. Now, when you actually sort through the details of it, what that means is your more mundane ideas of smoothness will be the same. I mean, that when you look at the formulas for the vector field, it's got smooth component functions that will work out of this definition. But at the same time, this definition is less clumsy than that. We define smoothness of manifold maps once, and then, yeah, we don't have to keep redefining smooth in different contexts. Is a point which is made powerfully by this wonderful book, Principal Bundles. Advertisement. Actually, I was not paid for this advertisement, but Stephen Bruce, S-O-N-T-Z, how do we say this? Sans? Santiz? Certainly wrong. Stephen Bruce S. Yes. Anyway, this is a great book. He really, at first glance, I thought it was a book about things I already knew. But when I read it, I realized he's taking the time to really emphasize what's defined badly in other books. In a gentle, polite, respectful way, but he's basically, he has things like, different authors keep giving different definitions of smooth for every these different objects. This is not needed. because these are still just maps from one manifold to another. So if we take a more categorical perspective, we've already defined that. So he really sells, there's a lot of low-level category theory in that book, which is useful. Just really efficiency of language, not category theory for category theory's sake either. No offense if you like that. So a section of the tangent bundle is a tangent vector field. You can guess a section of the cotangent bundle is a differential form. Or it's a one form, it's a covector field. A section of the tensor bundle would be a tensor field. So this is really nice because now we've actually got a home for these things we talk about. If you notice, if you watch me carefully, you'll notice that I don't always define the space in which the tensor lives or the differential form lives. I'll work with them at a point, but if you really watch me carefully, I never actually gave a name for the set of all vector fields. Maybe I did. Sometimes I call it. Actually, I can't resist. Sometimes I'll call it this. Right. Which you could say is sections of the tangent bundle. This is a kind of typical notation, sections of the tangent bundle. All right, great. So tangent bundle, cotangent bundle, tensor bundle, these are all examples of vector bundles. What is a vector bundle? By the way, something I haven't said yet is it may or may not be the case that a global section exists in the interesting sense. Okay, if you've got a coordinate neighborhood, what's a section? How about S of p is equal to p comma partial x1? Right, just use the coordinate vector field. That gives you a section, right? So if you had a global coordinate system on your manifold, you could do something like p comma partial x1. That would be a global section. But not all manifolds permit global coordinate systems, right? Sometimes you, by necessity, need more than one coordinate system to cover the manifold. So you can't always just use a global coordinate system to give you a section of a manifold, of a tangent bundle. And in fact, the inability of you to find global sections to certain manifolds, to the tangent bundle of certain manifolds, is detecting non-trivial topology in the manifold. A well-known theorem says that there does not exist, and that's not, I need to be a little more careful in my language. So there does not exist a global everywhere non-zero section of the tangent bundle to the two-sphere. What's that?
I have looked that up, and it's called the
Yes, the Hairy-Ball theorem. Yes, this is true. Although I take great pains to never say that. But yes, because students are students. Let's see here. But yes, it does in fact have that name. You got me. And like my.
I just looked that up, and it's a very impressive result.
Yeah, my advisor always would start talking about like imagining having hair over your whole head and trying to like comb your hair in such a way that you had no, like was it colic or whatever? So no part, because a part would be a place where you changed from going this way to that way, which would there had to be zero in between if you got smoothness. But I don't know. Yeah. So, in other words, there does not exist a global section. But you can always find local sections. You can always find local sections to the tangent bundle because you can always take coordinate charts to the manifold and do what I just said, like p comma partial x1. That gives you a local section. Obviously, when you try to paste those together and keep things non-zero, something goes awry for something like a sphere. All right, so what is a vector bundle? Generically speaking, definition, vector bundle is essentially a triple. It's a manifold, it's a vector space, and it's a map. Oh, I'm sorry. It's a. That's not it yet. It's more than that. It's a manifold. It's a total space. It's a vector space, and it's a map. And I think that's enough. That's enough. That's essentially a vector bundle. And the point is that, well, there exists U subset of M such that, and oh, sorry. I could open this book up and give you a careful definition, but I'm going to give you a sloppy one instead because it'll suffice. So what is a vector bundle? I mean, you've got this mapping pi that goes from the total space E to M. M is usually called the base space. For physical applications, I usually think of M as being space-time. So you got this projection from E to M such that there exists U, subset of M, where pi inverse of U is diffeomorphic, I suppose, to U Cartesian product of the vector space. So a vector bundle is something that, well, I mean, we can say more than this. I think we can say more than this. We can actually say that pi inverse of P is in bijective correspondence with P Cartesian product of the vector space. Yeah. Uh-oh. Oh, this is a joke. This is a joke.
No, that's really
This is so definitely a pun. I would be shocked if this wasn't a serious question. Go on.
So I'm just looking up other stuff on like.
Go on.
I'm looking up stuff on the Harry Potter.
Sure.
It says that something to combat that is the fact that if you have a two-torus, a regular torus, is you can actually comb it, like it works.
Oh, yes.
But why is it? Which part is being broken about that?
Okay, so the two torus, T2, also known as S1 cross S1, has theta beta. No, that's a mapping from T2 to, 0 to pi squared. I mean, or R2 if you like, okay? So you've got the pairs of coordinate angles. That's a global coordinate chart on the torus. And so what's the global section? How about, S of P equal to, P comma partial theta plus partial beta or something like that, I guess. Or maybe I could just do partial theta. Probably should just do one, yeah. That's everywhere non-zero on the two torus. Or you could do that would be another global section, and those would correspond to, if I could foolishly try to draw them. So depending on, I mean, one of these, right, one of these is like beta, and the other one is like the theta, right? So the partial theta one is something like this. Right? And then this section, if I were so foolish as to attempt to picture it, it's something like, like this. I can't. I mean, here's the integral, integral curves of the vector fields that are global.
I mean, what specifically, like mathematically, here, like enables to do
What makes that different than the two-sphere? That is, well, I mean, this one is, for one thing, it is clearly a Cartesian product but that's not quite it. I don't know, that's a really good question. I think understanding the answer to that question is understanding topology as it relates to these problems. It was essentially a corollary of the Gauss-Bonnet theorem that relates the curvature of two-dimensional manifolds to the topology as indexed by the Euler characteristic. So a corollary to the Gauss-Bonnet theorem has to do with the index of vector fields, which has to do with these non-zero. I'm not sure that's. I'm not sure I can come up with a simple answer. I mean, I can picture them.
Yeah, I mean, that's the point.
It's definitely global sections. In fact, there's two of them. And what's that?
I don't think the torus have a global section.
There's the global section right there. It's non-zero everywhere. Because it's got a global coordinate chart. Anytime I have a global coordinate chart, I can form a global section.
Global coordinate chart.
Oh, that is true. On the two-sphere, I cannot find a global coordinate chart. I just wrote a global coordinate chart. It's theta beta. I think so. Oh, you're worried about the...
I mean...
Yeah. I'm sorry. You're right. I mean, I have the... I'm sorry. I'm an idiot. The fall from... I get trouble with the injectivity on the full circle. Oh, fine. Fair enough.
I mean, the torus is compact. You cannot have a homeomorphic map to a from a compact set to a non-compact space.
Oh, yeah. I'm not saying that that's a surjection either, though.
So I just say about the non-existence of a global coordinate chart of a torus. Not the global section.
Well, I suppose neither the
Yeah,
neither the sphere nor the torus has a global coordinate chart. Fair enough. But
you're right about a global section.
the global sections I've pictured. Yeah, so I mean, it's subtle. It's just subtle. I don't deny it. I mean, to get an atlas for this the one sphere, also known as a circle, you can delete the North Pole or the South Pole, and get, you can get basically a coordinate chart on everything except for one point removed. It's just a stupid point, gets you in trouble with injectivity. So if you take that atlas, there's also a construction with the Cartesian product of manifolds. There's the product of manifold. So like if I have manifold M, manifold N, or say M1, Cartesian product M2, this is a new manifold M, where the coordinate chart on P comma Q is, P1 comma P2 is guess what? It's X1 of P1, X2 of P2. And if you have, U1, Cartesian U2 is the U for X. And then things of this form, U comma X, is something in the atlas for M1 cross M2. So forming an atlas for the Cartesian product of manifolds is not particularly difficult. You just take the Cartesian product of take the Cartesian product of the coordinate charts that you already have for the factors of the Cartesian product. And so sorting through that idea for S1 cross S2 is actually what technically would be needed to show that, in fact, my alleged global sections are actually global sections. I mean, fine. I don't know. Oh, now you've got me worried. Anyway, I'm going to move on. So this is a vector bundle. attach over each point a vector space in a smooth way. Locally, the vector bundle is isomorphic to the Cartesian product of the manifold with the vector space. So you're basically just gluing a copy of the vector space over each point. And that's kind of it. Then we get to the concept of what's called a principal bundle. Let's talk about principal bundles for a bit here. What is a principal bundle? Where'd I put my juice? Is it hiding here? Oh, yes, it has. So a principal bundle is, by the way, all of these are fiber bundles. In fact, what is a fiber bundle? Generically speaking, a fiber bundle over a manifold is something that is got, so if you have base space M, you've got total space E, and you've got some sort of local diffeomorphism to the Cartesian product of your fiber and the manifold. So more generically speaking, a fiber bundle, something like M, E, F, pi. And so you've got pi going from your total space E to your manifold. You've got the inverse image of, a subset of the manifold is diffeomorphic to U Cartesian product with F. But here, this is itself a manifold. So you could talk about fibers being manifolds. And a fiber bundle with fiber F, it would be something that is locally diffeomorphic to the Cartesian product of your manifold with the fiber. So in the case that the fiber is a vector space, you get a vector bundle. All right? So that's the more generic notion of fiber bundle. And the term fiber, it's all because really we have pi inverse of P is, up the diffeomorphism, P cross what? P cross the F. So again, the intuitive picture is just that we're gluing a copy of the fiber above each point in some sort of systematic way. If the whole space, I should mention this, if E is equal to M cross F, then this means that it's a trivial bundle. So a Cartesian product is the base case. It's the most stupid example of a fiber bundle. That's when we just glue a copy of F in the same way for each point in the manifold. It's the trivial case. So, all right, so principal fiber bundle. What's a principal fiber bundle? What's that? I'll try to be careful. Uno momento. Por favor. All right. He says, we say that P is a principal bundle over M. P is principal fiber bundle over M with structure group G. M is the base space. And P is the total space instead of E. We're using P now where I was using E, all right? P is the total space. And pi is the bundle map. So usual notation for this is something like G, P, M, pi. All right. He says here the horizontal inclusion map is not unique. It is any G equivariant diffeomorphism of G onto some fiber in P, and so is determined by the image of E, which is the identity in G and P. Maybe I should go back a few more pages. So before this, he describes how to build a principal fiber bundle by looking at a Cartesian product of a Lie group and a manifold. And maybe that's worth looking at for just a second before I give this definition more formally. So his starting point, and this was actually the starting point my advisor took, and course I had on these things. It's probably a good place to start. But so discussion. So what you could do is you start with M, with Atlas, U alpha, and I'll use his notation, phi alpha. I've been using X sub alpha for that, but we'll use phi now. Coordinate chart. And a cocycle. Cocycle, what on earth is a cocycle? G beta alpha, which is going to be a mapping from U alpha intersect U beta to G, where this is a given Lie group. What's a Lie group? A Lie group is a group, which is also a manifold, such that the operations are smooth with respect to the notion of manifold smoothness that I've talked about today. So the multiplication on the Lie group is a map from the Cartesian product of G with itself. So if G is a manifold, I described to you the manifold structure of G cross G over there. So we could talk about smoothness of a map from G cross G to G, which would be the multiplication smoothness. Then the inversion map would also be a map from G to G, which we could talk about the smoothness of. So to say that it's a Lie group is to say that the multiplication and the inversion maps are separately smooth mappings from G cross G to G and G to G. Lie group. All right. He says, however, we do not necessarily have a representation of G acting on a vector space, though we could be using a cocycle that comes from a given vector bundle. Oh. Rather, we will use the fact that any Lie group always acts smoothly on itself by multiplication on the left. But this is not a group action unless G is equal to E. So we now define smooth functions G tilde beta alpha, mapping from the image of phi alpha under the intersection of U alpha with U beta, Cartesian product with G, to phi beta, U alpha intersect U beta, Cartesian product with G, by the following formula: G tilde beta alpha of phi alpha of X, comma G, is equal to phi beta of X, comma G beta alpha of X times G. And that's for all X in the intersection and all G in G. All right, what's going on here? So then what? He says, we wish to emphasize that the expression G beta alpha of XG is the left action of an image of a cocycle.